Today we're going to start talking about congruences. So I'm going to give you a very simple definition that we're going to use throughout this course. And this is the definition. So we say that A is congruent to B modulo N if and only if N divides A minus B. Okay. So two numbers A and B are congruent modulo N if their difference is a multiple of N. Okay. Now, because I'm lazy and because it takes too much energy to do 3 lines, I sometimes just write it like this: A equals B modulo N. I write equal, I say equal, I mean congruent. Okay. So that's one thing. The other thing is sometimes I write it like this. I write A is equal to B modulo N. This is the same thing. Again, it's just me being lazy and not wanting to write all of this. Okay. So, for example, 12 and 22 are congruent modulo 10. So we can write it like this. I can say 12 is congruent to 22 modulo 10. So basically what we mean here is that if we ignore multiples of 10, these two numbers are equal. Right, so their difference in this case is exactly 10. And of course, 10 is a multiple of 10. So they're congruent modulo 10. And I can also say that 112 is congruent to 22. Okay. We're going to have a very simple theorem first, and then we're going to build upon that. So this is my first theorem. I say that A is equal to B mod N if and only if when I divide A and B by N, I get the same remainders. So A and B have the same remainders when divided by N. Okay. So this is pretty easy to prove. Again, this is if and only if, so I have to prove both sides. The first side, suppose that A is equal to B modulo N. What does that mean? That means that N divides A minus B. So A minus B is going to be some number, let's call it K times N. Okay. I want to show that A and B have the same remainders when divided by N. And by the way, just imagine that N is not 0, right? So none of this makes sense if N is 0. So I want to show that A and B have the same remainder. I know that every number can be written as a quotient and a remainder when divided by N. So I can write A in this form. I can write N as Q times N plus R. Okay. But what does this tell me about B? Yeah. So B is just going to be Q minus K times N plus R, because their difference is just Kn. And now you can see that, of course, they have the same remainder, right? And again, this was the unique remainder that is between 0 and N minus 1. Okay. So one side, this side, was quite easy. If two numbers are equivalent or congruent modulo N, or as I just say, equal modulo N, then they have the same remainder when divided by N. Now let's do the other side. Suppose that they have the same remainder. What does that mean? It means that A is something, let's call it Q1 times N plus R, and B is Q2 times N plus R. They have the same remainder R. Okay. So what is A minus B? It's just Q1 minus Q2 times N, right? The R's cancel out. So this means that A minus B is a multiple of N, which is the same as the definition that we had. So A is equal to B modulo N. Okay. So probably the simplest theorem in all of this course. Honestly, we sometimes even use this as the definition. So when we say two numbers are congruent modulo N, what we mean is that if we divide them modulo N, if we divide them by N, we will have the same remainder. Okay. Great. So this means that if I look at my numbers modulo some number N, I'm actually dividing or partitioning the set of all integers into N different sets. The integers that have a remainder of 0, a remainder of 1, a remainder of 2, so on to a remainder of N minus 1 when divided by N. So all I'm doing here when I'm talking about congruences is that I'm saying I don't care about the entirety of this integer. I just care what its remainder is when I divide by N. Okay. So one example of this that we have already done in a lot of problems is when N is 2. So when N is 2, I'm basically saying that I only care if the remainder of a number when divided by 2 is 0 or 1. So I only care if the number is odd or even. If that's all the information that I care about a number, I can do my calculations modulo 2. Okay. But this congruence actually has a lot of nice properties. It's an equivalence relation. That's why I'm kind of treating it like equality. And that's why I'm lazy. I don't write it with 3 bars and so on. But let's just write some of these properties. And because I don't have a great memory, I have to look at the book for this, because otherwise I will forget some of them. And all of them are trivial, actually. So this is another theorem. I think this is, yeah, theorem 4.2 in the book. It says this. So suppose that I have some integer n greater than 1. And let's say I have a bunch of other integers a, b, c, d. Okay. So we have these properties. Property, oh, it's weird that to use a and then we're using a for the number as well. Okay. So the first property is that a is equal to a modulo n. Can you believe this? This is so hard. The second property is that if a is equal to b modulo n, then b is equal to a modulo. Again, this is all just doing the definition, right? So n divides 0, so n divides a minus a. That's how you prove the first one. And for the second one, you're basically saying that if n divides a minus b, and also divides b minus a. I'm not going to prove the easy ones. Yeah, so we have this third one as well, which is if a equals to b modulo n and b equals c modulo n, then a equals c modulo. Pretty obvious. Okay, but the important point here is that this is just saying this congruence or equality modulo n is actually an equivalence relation. So it partitions all the numbers into a bunch of equivalence classes, and our equivalence classes are basically based on the remainders. What is the remainder of this number when divided by n? Slightly more interesting is this. If a is equal to b modulo n and c is equal to d modulo n, then a plus b is equal to c plus d. Okay. This is also trivial, but not quite as trivial as the previous ones. So if A is equal to B modulo N, what does that mean? It means that N divides A minus B, right? So I can say that A minus B is some K times N, okay? And similarly, I can say that C minus D is some other number, I don't know, let's call it L times N, right? So what is A plus B minus C plus D? It's just going to be, no. What am I doing? A is equal to B, C is equal, yeah, wrong order. This is what happens when something is too trivial. I write it wrong. Okay. So, yeah. What I wanted to say is that A is equal to C and B is equal to D. It's so trivial, it's not even worth it for me to start my brain. Okay. So, what do I know here? I know that A minus C is some multiple of N. I know that B minus D is some multiple of N. So A plus B minus C plus D is going to just be K plus L times N. So this is also a multiple of N, which means that A plus B is congruent to C plus D. Okay. Slightly less trivial is this one. What's the number? 5. Okay. Suppose that A is equivalent to B modulo N and C is equivalent to D modulo N. Then AC is equivalent to BD modulo. Okay. So I can do multiplication, basically. That's all this is saying. Why does this hold? Again, you just write the definitions. So A equals to B modulo N. What does that mean? It means that A minus B is some number, let's call it K1 times N. C is equal to D, so C minus D is some number, let's call it K2 times N. Now I want AC minus BD. How can I write this so that it becomes a multiple of it? To substitute B and C. Yeah, so I want to try to get rid of some of the equalities here. So I have this D here. Instead of D, I can write C minus K2N, right? So this is AC minus B times C minus K2N, right? And let's say, okay, I have A, B, and C right now. What is the next variable that I want to get rid of? Which one? Make your mind. Okay, let's get rid of B. Let's see what happens if we get rid of B. So I will have AC minus, instead of B, I will have A minus K1N. Okay, and here I have C minus K2. Okay, what am I getting now? If I just expand this, it would be AC minus, here I have another AC, right? But any other term that I get here already has N. So minus something, I don't care what that thing is, I'm too lazy, times N. Right. So this is 0. if you consider it modulo n, or so it's something times n. My laziness knows no bounds when it comes to doing any kind of calculation. I don't want to expand this. Okay. Yeah, as a special case of this, I can do this. I can say that if A is congruent to B modulo n, I can just multiply both sides by some constants. Then AC is congruent to BC modulo. Again, this is a special case of the previous one. Right? Because of course, C is congruent to itself. Okay, great. So, and of course, I can have a special case of this for addition as well. So I can say A plus C is also congruent to B plus C. This is also very easy to check. Okay. But now the question is, can I do the opposite of this? So you see, when I have that A and B are the same modulo n, I can multiply both sides of my equality by some constant C, or I can add a constant C to both sides. But can I do the opposite? Can I cancel a constant? Now, on the one hand, this is quite easy. So if A plus C is the same as B plus C modulo n, then A is the same as B modulo n. Right? Again, you can just write the definition. What does this mean? This means that n divides A plus C minus B plus C, but this is just A minus B. Right? So of course I have cancellation here. But can I do cancellation when I'm multiplying something? So can I have something like this? Can I say if AC is equal to BC modulo n, then A is equal to B modulo. Well, I mean, if you just think of the integers without the mod and so on, you already know that you cannot do this kind of cancellation if C is 0. Right. So for example, I have that 2 times 0 is equal to 1 times 0 modulo 3, but this doesn't mean that I can cancel the zeros. 2 is not the same as 1. Okay, so let me ask you something else. Let me ask you for the case where C is not 0. So imagine that AC is equal to BC modulo n, and C is not 0, also modulo n. Can I then cancel the C from both sides? No. No, still no. Why not? You can divide. Yeah, so let's try this. Let's try 2 times 4 and 2 times 1 modulo 6. Okay, these two are equal. You agree? Because 2 times 4 is 8. Its remainder when divided by 6 is just 2. And of course, 2 times 1 is just 2. Right? But I cannot cancel the 2 from both sides. Because if I cancel the 2 from both sides, I get that 4 is the same as 1 modulo 6, and it's not. Okay? So in general, the answer here is no. We don't have this. Don't do this. Okay. Great. But because I can multiply both sides by something, I can also have something like this. So I can say, if this is 8, I can say if A and B are the same modulo n, then A to the power of any number k is equal or congruent to B to the power of the same number k modulo. Again, this is just applying the rule that we had for multiplication. It's just that I'm applying it k times. So you can prove it by induction. Okay. But let's go back to this problem of not having cancellation. So if you've passed any courses on algebra, basically the reason I don't have cancellation here is that not all of my elements have an inverse, right? So in general, when I want to have cancellation, when I want to have something like this, so suppose AC is equal to BC, okay? If I want to cancel C, I can do it if I have some sort of an inverse for C, if I have a C inverse, because then I can just multiply both sides by C inverse, and then I can say this is one, so A is equal to B, okay? That's generally the idea that we have when we want to do cancellation. And this is the reason why we have cancellation in, let's say, real numbers, because every real number other than 0 has an inverse. And whenever I'm canceling it, I'm basically just multiplying both sides by its inverse. But the problem here is that some numbers don't have inverses, right? So what is an inverse? Or actually, we call it modular multiplicative inverse. Big words for a very simple definition. So this is very simple. So let's say that I have some modulus n and I have some number a. So A inverse is just an integer such that A inverse times A is congruent to 1 modulo n. And of course, this is when doing calculations modulo n. Okay, so fixing some modulus n, my modular multiplicative inverse, which I show as A inverse, is just some integer that if I multiply it by my original number A, I'll get 1. Okay. Now you can easily see that not all numbers have inverses modulo all other numbers. So for example, if my n is 6, this is the example we had before, and let's say my A is 2. Okay. I cannot find any number that can be multiplied by 2 and gives me 1 modulo 6. So there is no number x such that 2x is 1 modulo 6. Why is this? Because forget about the modulo part, 2x is always going to be an even number, right? So this side is even, this side is odd. If I subtract them, I will get an odd number, and an odd number cannot be a multiple of 6. So I can never find any number x such that 2x is equal to 1 modulo 6. So this means that 2 doesn't have a multiplicative inverse when I'm doing calculations modulo 6, which means that when I'm doing calculations modulo 6, I cannot cancel 2 from the two sides of an equality. Okay. But let's look at a different number. Let's say 5. Does 5 have an inverse modulo 6? So is there some x such that 5x is equal to 1 modulo 6? Give me the number. 5. Yes. What is 5 times 5? 25. Modulo 6, it would be 1 because it's 24 is a multiple of 6. So actually 5 is its own inverse, modulo 6, right? So if I have something like this, if I have 5a is congruent to 5b modulo 6, I can cancel the 5 from both sides because that's equivalent to multiplying both sides by 5, right? I can just say, well, these are equal, and I know that when two things are equal, I can multiply both sides by a constant. I'm going to multiply both sides by the inverse, which in this case is 5 itself. So I'm going to have 5 times 5a is equal to 5 times 5b modulo 6. But then 5 times 5 is 1 modulo 6. So instead of this 5 times 5, I can just write 1. So A is equal to B modulo 6. So you see, sometimes I can cancel. In this case, because 5 has an inverse, I can cancel 5 from the two sides. So this is basically what I'm doing. Okay, so I could not cancel 2, but I can cancel 5. So in general, I want to figure out what are the numbers that can be canceled. If I'm doing my calculations modulo n, so in this case, for example, I'm doing calculations modulo 6, what are the numbers that are like 5 that I can cancel from both sides? Right. So to do that, we're going to go back to graph theory, actually. Okay. So here's some weird thing we're going to do. Consider all the numbers modulo n, and we said that instead of having all of them, we just represent them by their remainder. So if I want to have a bunch of numbers that give me all the possible remainders, I can say when calculating something modulo n, basically all of my numbers are these. My numbers are 0, 1, 2, so on to n minus 1, right? Because I'm ignoring everything other than the remainder modulo n. Okay. I'm going to define a function here, and it's a very simple function. I'm going to say, suppose I have some number a. I want to just shift all of my numbers by a positions. So I want to have a function, let's call it s sub a. So this is shifting by a positions. And what it does is that it takes any number x in this range, and it just maps it to x plus a. And all of my calculations are modulo n. Okay, so it just wraps around, basically. Let's do an example. Let's say my n is 6 and my a is 2. So I will have the numbers 0, 1, 2, 3, 4, and 5. These are all the possible remainders that I can have modulo 6. And then when I apply this shift, I'm basically adding 2 to every number. So 0 is mapped to 2, 1 is mapped to 3, 2 is mapped to 4, 3 is mapped to 5, 4 is mapped to 0. Because 4 should be mapped to 6, but 6 is the same as 0. I'm doing calculations modulo 6. And 5 is mapped to 1. So this is the function that I have, the function that maps the numbers in the top row to the numbers in the bottom. Okay. Here's what I claim. This function is a permutation. Do you agree? I'm just shifting everything. It's very obvious. It's a permutation. If you want to really prove it, you can prove that it's 1-to-1 and onto, and you can prove it using these trivial things that we had here, right? So it's a permutation. But what do we know about permutations? We know that we can create a graph for every permutation, where I'm basically putting one vertex for each element, and I'm putting a directed edge from I to j if I is mapped to j. So let's create the graph of this permutation. So I have 0, and 0 is mapped to 2. And then 2 is mapped to 4, right? And 4 is mapped to 0. Then I have 1, which is mapped to 3, which is mapped to 5, which is mapped to 1. Okay. Now, in general, when we were talking about permutations, we said that the graph of every permutation is just a bunch of disjoint cycles. And in this case, we're getting that too. We have 2 disjoint cycles, right? Okay. So I want to see whether this number a has an inverse modulo n. What does that mean? That means that can I have ax equals 1 modulo n? But what are all the numbers that can be written as ax? These are all the numbers that are in the same cycle as 0, right? Because this is 0, this is A, this is 2A, and then, of course, if I had a bigger example, then I would have 3A, 4A, so on. So I will have any X times A. And all of them will be in the same cycle as 0. Okay? So whenever I'm asking, does this have a solution? What I'm asking is, let's create the permutation for this particular A. And is 0 and 1, are 0 and 1 in the same cycle? In this case, 0 and 1 are not in the same cycle, right? So the first cycle, this one, is the cycle of all multiples of 2. And since 1 is not in this cycle, 1 is not a multiple of 2. So there's no x such that ax is equal to 1. 2x is equal to 1 modulo 6. Okay. Great. But now we can talk about the structure of these cycles. So let me do a different example. Let's say my n is 6 and my a is 5. Okay. So I'm not going to do the permutation anymore. I'm just going to draw the cycles. So 0, let me draw it in a different color. So 0 is going to be mapped to 5 because I'm adding 5 every time. 5 is going to be mapped to 4 because 5 plus 5 is 10, modulo 6, that's 4. And then 4 is going to be mapped to 3. Every time I'm adding 5, by the way, adding 5 is like subtracting 1 because I'm doing modulo 6. And then this one will be mapped to 2. This one will be mapped to 1. And this one will be mapped to 0. So if my A were 5, I would just get one cycle. And because I get only one cycle, of course, 0 and 1 are going to be in the same cycle. So there is going to be a multiple of A, a multiple of 5 in this case, which gives me 1. Because I start at 0, I'm adding 5 every time, and eventually I'm getting to 1. So 1 is going to be equal to some multiple of 5. Okay? Now, what we want to figure out is, when do we get this situation? When do we get the situation where 0 and 1 are in the same cycle? Okay. So first of all, I want to claim that all of my cycles are going to have the same size. Why is that the case? Because each cycle is basically just a shift of the other cycle, right? So I can have this cycle. If I shift all the numbers by 1, if I just add 1 to all the numbers, I will get this cycle. Right? And in general, no matter how many cycles I have, I can look at the minimum element of each cycle, and I can say each cycle is a shift of the cycle that starts from 0, where I'm just adding the minimum element of this cycle to every element. Okay, so all of my cycles are going to have the exact same size. Okay, what is that size? Not necessarily. So we have to kind of maybe consider two cases. So because I want to get the n over a, suppose that a is a divisor of n. If a is a divisor of n, then the size of each cycle would be n over a, and I will have exactly a cycles. So in this case, 2 was a divisor of 6. So the size of every cycle is 6 over 2, which is 3, and I have exactly 2 cycles. But not in this case, right? Yes. So we have to look at the GCD of A and N. Okay. If the greatest common divisor of A and N is D, so let's say GCD of A and N is D. Okay. Then I claim that the number of cycles is going to be D. Okay. Number of cycles is D. And of course, the size of each cycle would be n over t. Okay. Why is this the case? Well, it's pretty easy to prove it when a is a divisor of n, right? So if n is a multiple of a, such as this case here, n is 6, a is 2, n is a multiple of a. So I'm going to have like 2 times 2, 2 times 3, so on. And as soon as I get to 2 times 3, that's already 6. So my cycle closes because 2 times 3 is just 0, right? So in general, if a divides n, let's say n is something like k times a, okay, what would happen here? What I'll get is a cycle like this. I just want to look at the cycle containing 0. I'm going to start at 0, and then I'm going to add a every time. So I get a, I get 2a, 3a, so on, until at some point, I get k minus 1 times a, right? And then ka is the same as 0, because ka is just that. Okay, so this is what's going to happen if a is a divisor of n. Now, suppose that a is not a divisor of n. We want to just extend this to the general case. First of all, what are these numbers that I'm creating in this cycle of 0? Basically, the numbers I'm creating here are multiples of a, but I'm subtracting multiples of n from them, right? So I'm going around this cycle every time I'm adding a. But I only care about the remainder modulo n. So whenever my number gets bigger than n, I'm removing a multiple of n from it, right? So any number that I'm writing in this cycle, in the cycle containing 0, is a linear combination of a and n. Do you all agree with that? Okay. So if it's a linear combination of a and n, we've already proven that the linear combinations of a and n are just the multiples of the GCD of these two numbers, right? So any number that is going to appear in this cycle, it's a linear combination of a and n, so it's a multiple of d, because d divides both a and n. But I can also prove that d itself appears in this cycle, right? Because remember, if I have d is the GCD of a and n, then d can be written as some linear combination of a and n. So d can be written as some ax plus ny, right? But what does this mean? If I look at it modulo n, it means that d is equal to ax modulo n, right? Just cancel the ny. So if I'm creating this cycle where I'm starting with 0 and I'm just seeing all the multiples of a, at some point I'm going to see ax, which means at some point I'm going to see d. Okay? So again, among all of my cycles, I'm looking at the cycle that includes 0, and that cycle is going to include the GCD of a and n. And of course, if a cycle includes a number, it also includes any multiple of that number, right? Because if d is ax, what does this mean? This means that I start in the cycle that contains 0, and I keep going, and let's say I go for x steps, right? So if I go for x steps, I get to d. But then I can go for 2x steps, and I'll get to 2d, right? In general, I can go for kx steps, and maybe when I do this, I will even wrap around, who cares? But I will get to kd, okay? So what I proved here is this. If I fix an n and an a, and then I create this permutation and look at its cycles, the cycle containing 0 is going to consist exactly of all the multiples of the GCD of a and n. Okay, so every multiple is in that cycle, and everything that is in that cycle is a multiple of d. Okay, so how many cycles am I going to have? I'm going to have d cycles, and each of them is going to have a size of n over d. Because again, remember that I'm only looking at the numbers as remainders. I'm only looking at the numbers from 0 to n minus 1. I'm asking how many multiples of D are between 0 and n minus 1, well, n over D, right? And then the number of cycles is, of course, just the total number of numbers divided by the size of each cycle. So it's just, okay. What we proved here is this. So this is our theorem. The number A has an inverse, has a modular multiplicative inverse modulo n, if and only if the GCD of A and n is equal to 1. Okay. Because I said I have an inverse if 0 and 1 are in the same cycle, but if 0 and 1 are in the same cycle, then everything is in that cycle. Because I have 1 in that cycle, so I have 2, I have 3, everything is in that cycle, right? And so the GCD should be 1. Okay, but this whole cycle business, I mean, it's a valid proof, but I did it only to give you intuition. I can prove this kind of more easily, like in 2 lines as well. So what am I doing? If I want to find an inverse for A, that basically means that I want to find some x such that AX is equal to 1 modulo n, right? But what does this mean? This means that n divides AX minus 1, right? So basically I can write this as like AX minus 1 is some k times n, or actually, let me call it y. It's some y times n, right? Just swap everything. So AX minus NY is equal to 1, right? So if I can write 1 as a linear combination of A and N, then I can find an X where AX is equal to 1 and vice versa. But I know that I can write 1 as a linear combination of A and N if and only if the GCD of A and N is 1. Okay, great. But what else can we say? So suppose that the GCD is not 1. I know that I cannot cancel the number A from 2 sides of an equality anymore. If it's like, if I have AB equals AC, I cannot cancel the A. But can I get something? Can I get maybe, let's say, a weaker result, a weaker kind of cancellation? And the answer is yes. So we have this. This is another theorem. So I want to say that suppose AB is the same as AC modulo n. And let's say that D is the GCD of A and N. Okay, so the GCD is not necessarily 1. I want to say that I can cancel A from both sides. I can write it like this. I can say then B is the same as C, but no longer modulo N. I'm going to say modulo N over D. Okay. Now, again, what you can do here, and what I love to do, but I don't have time for it, is to look at those cycles. So now you have to look at 2 different permutations. You have to look at the permutation that you will get by constantly adding A when you're doing calculations modulo N, and you have to look at the permutation when you're doing calculations modulo N over D. So that's going to give you 2 different graphs, and then you can argue that B should be equal to C modulo N over D. But I'm going to give you a much nastier proof, right? So AB is equal to AC modulo N. What does that mean? That means that N divides AB minus AC. Okay, so A times B minus C. Okay, so let's say that A times B minus C is N times some number K, because N divides it. Okay, now let's divide both sides by D. What do I get here? I'll get A over D times B minus C is N over D times K. Okay. So this N over D divides this part, right? Because this left-hand side is N over D times some number K. So N over D divides A over D times B minus C. Okay, what is the GCD of these two numbers? What is the GCD of N over D and A over D? This is 1. Because remember, D was the GCD of A and N, and we had this theorem that if you just divide both numbers by their GCD, the resulting GCD, the GCD of the resulting numbers is 1. Okay? So now I can apply Euclid's lemma, because look, I have a number here which divides the product of two other numbers. And its GCD with one of them is 1. So it has to divide the second one. So I just apply Euclid's lemma at this point. And I say by Euclid's lemma, N over D divides B minus C. But this is exactly what I wanted to prove, right? I wanted to prove that B is equal to C modulo N over D, which is by definition the same as saying N over D divides their difference. Okay. Now, again, honestly, whenever it comes to these proofs, I prefer going back and looking at the graph. That gives you so much more intuition. Everything is much nicer there, but this kind of proof is shorter. And I don't have much time in this class, so I have to give you the short. Okay. What else? Well, there are some techniques that you should know about, which makes your life much easier. And one of these techniques is fast modular exponentiation. So suppose that you want to find the remainder of, let's say, A to the power of B. So I use the C++ notation here. Let's say I want to find the remainder of A to the power of B when divided by C, right? And suppose that these are large numbers. So I want, I don't know, something like this, modulo 7. So one way would be to actually compute this huge number and then do the division. But that's the stupid thing to do. You shouldn't do that. And imagine if this was even more complicated. Imagine if I had something like this. So A to the power of B to the power of C, all of it modulo D. Yeah. Or even more interesting, suppose I had this. Okay. Yeah. What would you do in these cases? Well, this one is something that we will come back to in the next session because it needs a little bit more theory. But this one is quite easy to compute. So here's the thing. I can use this last trivial equality that I had here. Where is it? Oh, this one, right? And I also have this for multiplication. So basically, suppose that I want to find A to the power of B. I can just find A to the power of B over 2 and multiply it by itself, right? But instead of calculating A to the power of B over 2, I can just calculate its remainder modulo C. So I can always keep working with numbers that are between 0 and C minus 1. I never have to work with large numbers. And in general, my algorithm would look something like this. Please give me, I want a monospace font. It really hurts me to write algorithms in non-monospace fonts. Okay, so no, it doesn't work. Okay, so let's say I want to have a function like this, and this is supposed to return a to the power of b modulo c. Okay, so I can have a simple base case. I can say if b is 0, just return 1. Okay, and I'm assuming that a is not 0 here, so maybe let's do this first. If a is 0, return 0. Okay, and sure, I can do that too. Actually, I can just say a and b. Yeah, I can say a can be modulo c. That's fine. But let me just continue with this. I want to say if b is 1, so I just have a, so I just return a modulo c. And in any other case, I find a to the power of b over 2, and I multiply it by itself. Now, again, I have to do a case where is b odd or even, right? So let's say that, I don't know, let's call it d is a to the power of b over 2, and I'm assuming integer division here, modulo c. And then I'm going to multiply d by itself. I'm going to say, take the remainder modulo c. Okay. And then I have to do another case. I have to say if b is odd, then I have to multiply d by a, and then take it modulo c. And then you return d. Okay. So pretty easy. And generally, I can also, if I don't want my a to be too big, here in this case, I can also say, make sure a is at most c. Okay. So this does very few multiplications. And of course, the important thing is it always keeps your numbers, the results of the exponentiations between 0 and c minus 1. And it's correct because of all the lemmas that we had for exponentiation and multiplication also. Okay, but let me show you something a little bit more interesting. I think this is something that you were taught in primary school, and it's this rule for divisibility by 3. So they tell you a number is divisible by 3 if and only if the sum of its digits is divisible by 3. Of course, when you're 6 years old, this looks like magic, but it's pretty easy to prove. Right? So let's say I have a number and my number is written in binary. Or, well, no, actually, this is not binary. So my number is written in base 10. So what is my number? If I have a number in base 10, and let's say it's something like this. So suppose that I have C0, C1, C2, so on to CK. Let's say these are the digits of my number. When I do this, I mean, it's just digits of one number. So what does this number actually represent? This is C0 plus C1 times 10 plus C2 times 100, right? So on to CK times 10 to the power of k. So basically my number is the sum of Ci 10 to the power of I, where I goes from 0 to k. Okay. And what I'm saying here is this. I'm saying this sum of Ci times 10 to the power of I is congruent to just the sum of Ci, if I take it modulo 3. Right? So what is 10 modulo 3? 1. So what is 10 to the power of any number I modulo 3? It's 1. So because 10 is the same as 1 modulo 3, then for every I, 10 to the power of I is equal to 1 to the power of I, which is just 1 modulo 3. So these 10 to the power of I things, they don't matter. So sum of Ci times 10 to the power of I is the same as the sum of Ci modulo 3. By the way, we have the same rule for 9. Right? And now you can find similar rules for every other integer. So suppose that I want to find a rule like this for divisibility by 5. I just write my number in base 6, right? And then I will have 6 to the power of I here, which is the same as 1 to the power of I. So for any number, if I want to check divisibility like this, I can write my original number in just some base. If I want to check divisibility by n, I can write my number in base n plus 1. And then I can say the number is divisible if and only if the sum of its digits is divisible. Right? And in this case, actually, for 3, I didn't even need 10. I could just write it in base 4. Okay. What if my number is written in base 10, but I want to check divisibility modulo 11? What can I do in that case? Yes, but well, I can also do something like this. So let's say I'm doing sum of Ci times 10 to the power of I, and I'm doing this modulo 11. Okay. What is 10 to the power of I modulo 11? Here's an interesting thing. 10 is the same as minus 1 modulo 11, right? So 10 to the power of 2 is going to be the same as 1 modulo 11. And then 10 to the power of 3 is again minus 1. And so on. So I can replace this 10 basically with minus I. So this is the sum of Ci times minus 1 to the power of I. Which means that if you want to check whether a number is divisible by 11, you just look at its digits, you add the first digit, subtract the second one, add the third one, subtract the fourth one, and so on. And if that resulting number is a multiple of 11, then the original number is also. Okay. Now, what else can we do? Okay, so I can actually extend this to any polynomial, right? So I can have this theorem. So suppose that P of X is a polynomial. And here I mean a polynomial with integer coefficients. Right, so let's say P of X is something like C0 plus C1x plus C2x squared, so on to CK xk. Okay. Then I can say this. I can say if A and B are congruent modulo n, then P of A is congruent to P of B modulo n. But of course, I had this rules of preserving congruence for addition and multiplication. Just keep applying them until you get this polynomial. But then this theorem also gives us all of these cases, all of these previous ones as special cases, right? Because just put x equal to 10, you get Ci times x to the power of I, here and put x11 or -1, you'll get this. So for any polynomial, I can generally say that if a is equal to b, then evaluating the polynomial at a will give me the same result as evaluating the polynomial at b. Okay. I'm going to unlock an achievement that I never thought I would unlock. Most of you are Chinese, right? I'm going to teach you about the Chinese remainder theorem. That's amazing. Okay. So look, we want to look at the linear congruence, or this linear equation. AX is congruent to B modulo N, right? So first of all, when does this have a solution? So we looked at the case where B was 1. We looked at the case AX equals to 1, and we said that it has a solution if the GCD of A and N is 1. But what if instead of having a 1 on this side, I just have B? Okay. So I claim that this linear equation is solvable and let me give a name to the GCD of A and N. Let's call it D. This equation is solvable if and only if D is a divisor of B. Again, this is just the same problem as before. We're going to look at those cycles. So consider the permutation that maps every element to that element plus A, right? So I'm going to have this cycle which starts with 0, and then it goes to A, it goes to 2A, 3A, so on, until at some point it comes back, right? And these are calculations modulo N. So if I want to solve AX equals to B, what I mean is that B should be in this cycle, right? But we talked about this cycle. What is this cycle? This cycle is just all the multiples of the GCD. So if B is in this cycle, then B is a multiple of D. Okay, so this is nothing new. This is just the same thing that we've seen with cycles before. But how many solutions will I have? And again, imagine that my numbers are modulo N, so I'm thinking that I have only N numbers. I have the numbers from 0 to N minus 1. Because otherwise, of course, as long as I have a solution, I will have infinitely many solutions in integers. But I'm asking how many solutions do I have if X is supposed to be between 0 and N minus 1? So how many solutions does this linear equation have? Does AX equal to B have with X being between 0 and N minus 1? Yeah. So the thing is, I know that if D is not a divisor of B, then the answer is 0. But if D is a divisor of B, then the answer would be what? Exactly D, right? So the number of solutions is going to be 0 if D is not a divisor of B, and it's going to be exactly D if D is divisor of B. Why? So we've shown that it's 0 if D is not a divisor of B, and there is at least one solution if D is a divisor of B. But why do I have exactly D solutions? It's again talking about the size of this cycle, right? So this cycle contains all the multiples of D. It doesn't contain them in the normal order because it's actually all multiples of A, right? So it's like A, 2A, 3A, so on. But if I ignore the order, it contains all the multiples of D. So how many multiples of D do I have in this cycle? What is the size of this cycle? This is N over D, right? So I have a cycle of size N over D. Let's just consider this. I have this cycle, which starts at 0 and ends at 0, and its size is N over D. So it has N over D vertices and N over D edges. Okay. And I know that at some point in this cycle, I'm seeing the number B. Okay. So B is somewhere. So let's say after I've taken X steps in this cycle, I've got to B, which is the same as just saying that AX is equal to B modulo. Okay. But now I can take my X steps and then I can go another full circle around the cycle, right? So if with X steps I end up at B, I can also take X plus N over D steps. N over D was the size of the cycle. And I will be at the same point. I will be at the same point B. So A times X plus N over D is also B modulo N. But I can take my X steps and then I can go 2 rotations around the cycle or 3 rotations around the cycle or as many rotations as I want. So in general, I can say A times X plus any multiple, any number T times going the cycle is going to be equal to B modulo N. Right? But how many different values can this T take? D different values, because I want this whole thing to be between 0 and N. And every time I'm increasing my T by N over D, so I can do this D times. So I will have exactly D solutions. And by the way, these are the only solutions. Because whenever I'm looking at multiples of A, I'm just going around this cycle. So the only way that I can get to this point of the cycle is that I take X steps plus some number of complete cycles, right? There's no other way to reach here. So these are the only solutions. Okay, so we proved that if we have a linear equation of this form, AX equals to B modulo N, and if the GCD of A and N is D, then it's solvable if and only if the GCD divides B, and the number of solutions is going to be exactly equal to the GCD. Great. Now, suppose that instead of just having one such equation, I have 2. Okay. So consider this. Consider that I have AX or A1X is equal to B1 modulo N1, and A2X is equal to B2 modulo N2. Okay. And to make the matters a little bit easier, let's say that the GCD of N1 and N2 is 1. So N1 is relatively prime to N2. I want to solve this. And I'm going to even make it easier. Let's say that each one of these equations has only one solution. I want to make sure that each equation has exactly one solution, which would be the case if this D is 1, right? So I'm going to say, suppose that A1 is relatively prime to N1, and A2 is relatively prime to N2. So that I know that if I only had this first equation, I would have exactly one solution. And if I only had the second equation, I would also have exactly one solution. Right? But now I have both of them together. So I want to find one value for X that satisfies both of these equations. Is that always possible? Yes or no? So this one has exactly one solution, this one has exactly one solution. Can I find a solution for both of them together? Okay, so let's try this. Let's say A1x is equal to B1 modulo N1. Okay, what does that mean? That means that N1 times some number, let's call it K1, is A1x minus B1. And I know that I have exactly one solution for the second one. So N2 times some K2 is going to be A2x minus B2. Can I combine these? Or let me look at this in a different way. So let's say I look at the solution of the first equality here. So let's say I have some solution x0 or x1, and a1 x1 is equal to b1 modulo n1. Okay, so I have a solution x1 that satisfies this first one. But if x1 satisfies this, what happens if I add something to x1? So what happens if I add n1 to x1, for example? What is a1 times x1 plus n1? That's also a solution, right? So this is also b1. Right? So if I have a solution for my first equality, I can just keep adding n1 to my solution, and that gives me other solutions for the first equality. Let's do an example, actually. So let's say my first equality is 3x equals 4 modulo 7, right? Or modulo 5. I'm too lazy for 7. And let's say that my second one is 2x equals 1. Now I have no way, I have to say modulo 7. Okay. So n1 and n2 are relatively prime. This 3 is relatively prime to 5, 2 is relatively prime to 7. Okay. Now, so I know that 3x equals to 4 has exactly one solution modulo 5. What is that solution? It's 3. 3 times 3 is 9. And modulo 5, that's okay. So if I set x equal to 3, that's a solution for this one. But again, this is 3 modulo 5. So I can add 5 to it. I can set x to 8. And that's also a solution. Right? I can add another 5 to it, 13, 18, so on. These are all solutions. Okay. So what are the solutions to this? They're basically take this first solution and every time add 5. Right? But let's look at these solutions as cycles when we're doing calculations modulo this second number, modulo n2. So I'm doing calculations modulo 7, and I'm starting with the number 3, and every time I'm just adding 5, right? So I know that adding 5, that's going to give me a permutation. It has the cycles, all the good things that I already know. So I'm going to start with 3, and then the next one is 8, right? But 8 modulo 7 is 1, right? Oh, I already found my solution. Oh, right. But I keep adding. I add 5. So that would be 6, which is 6 modulo 7. I add 5 again. What is that modulo 7? I'm bad at this. It's 4, right? And then so on. Anyway, this creates a cycle, right? Actually, what is 4 plus 5? That's 9. It's 2 modulo 7. 2 plus 5 is 0. Yeah, and great. So this is actually the cycle that contains 0 and it goes all the way. So it will contain all the numbers. I'm really lazy. Okay. So what can I do here? Actually, let's not be lazy. You're right. Let's just do this. 0 plus 5 is 5. And then 5 plus 5 is 10, which is 3. So my laziness was just for one vertex. So I have this cycle, and all I want to do is find this number, find 1 in this cycle. And in this case, I did. Okay, so I want to find B2 in this cycle. Can I always do it? Yes. Why can I always do this? Because I'm assuming that N1 and N2 are relatively prime. So when I'm starting with some number and adding N1 every time, this is going to be a cycle that contains all of the remainders modulo N2. So I'm going to get all of the numbers here, including this number B2 that I'm looking for. So I'm going to find a solution that satisfies both of these. A1x is equal to B1 and A2x is equal to B2. Okay. And moreover, it's really easy now to prove that your solution is unique. It's unique modulo N1 times N2. Because of course you can add N1 times N2 to your solution and it will still be a solution. But there is only one solution among the numbers between 0 to N1 times N2 for this. Okay. And again, the uniqueness is just that you write all the possible solutions to the first one. You say that in this cycle, there is only one place where I have this B2. So there's only one X that satisfies this. Yes. Yes, well, but I want to say that I have a unique X, right? So the X here is unique modulo N2. But I don't understand your question. Ah, okay, great. So can we find this value exactly without doing all of this? Like, how would you find this value exactly? Think about that and think about the Euclidean algorithm or the GCD. But what I want to do here is I want to extend this and I want to get to the Chinese remainder theorem. So this is the Chinese remainder theorem. I want to say that, actually, let me just copy this. I want to say that instead of 2, suppose that I have R different equalities like this. So I'm going to say this. I'm going to say let N1, N2 to NR be positive integers. And suppose that every pair of them is relatively prime, such that for every I not equal to j, ni and nj are relatively prime. Okay. And then consider the system of linear congruences. This one. So I want to say that x is a1 modulo n1, x is a2 modulo n2, so on, and x is equal to AR modulo NR. Okay. I want to say that this has a solution and it has a unique solution modulo the product of the ni's, modulo n1 times n2, so on. Okay, first of all, why is this really an extension of the previous one? Because if you look here, I had something more, right? I had ax equals to b. But now I'm just saying something like this. I'm just saying x is equal to something. Why are these two things the same? Because here I was saying that a1 is relatively prime to n1, right? So if a1 is relatively prime to n1, a1 has an inverse. So I could just multiply this by the inverse of a1, right? So I can just multiply both sides by the inverse of a1. That will give me a1 inverse a1x is equal to a1 inverse b1 modulo n1, right? But now I can cancel the inverses. So even though I wrote this like this, I could instead just write it as x equals to something modulo n1, right? And here again, I could write it similarly as x equals to something modulo n2. Okay, so actually let's look at that for a second. So let's say that I have x equals something, let's call it a1 modulo n1, and x is equal to something else, a2 modulo n2. And let's say that n1 and n2 are relatively prime. I know that this has exactly one solution, modulo n1 times n2. That's what I've already proven because this is equivalent to this. I'm just changing the names, right? But what is that solution? Can you just give me a formula for that solution? Okay. Think about this. It's a very easy thing. Formula for the solution. Okay, let's go back to this one. So, because every linear equality that I wrote before is equivalent to this, this is an extension. Now I'm saying instead of two, I have R equalities. But why does this hold? Why does it have a solution and why is the solution unique? Well, take the first two and just merge them into one. Take the first two equalities, merge them into one equality, right? So if I only had this first part, if I only had x equals to a1 modulo n1 and x equals to a2 modulo n2, I know that this is equivalent to something like x equals to some a prime modulo n1, n2, right? I've already shown this, right? So I said that if I have these two equalities, they have exactly one solution. Let's call that solution a prime, right? And that solution is unique modulo n1 times n2. So instead of these two equalities, I can write an equality like this, where a prime is just the answer to these modulo n1 and 2. And then I can replace my first two equalities with this one, right? And all the conditions are still satisfied, so I have one fewer equality. So I keep doing this. I keep removing one equality at a time until I have two equalities, and I can just apply the base case. So this is just apply, and just take this theorem and apply an inductive reasoning to it. Or to be more specific, I'm doing infinite descent here. I'm saying that I'm removing, I'm reducing the number of equalities by one in every step. So it has to eventually end. Okay. Find this formula. It's so easy. It's very easy. Okay. Look. Suppose one of these is 0. Suppose that I have x is equal to a1 modulo n1 and x is equal to 0 modulo n2. What would you do? What is the solution here? Just find the solution for this and then find the solution for the opposite case where the first one is 0 and the second one is not 0 and add them together.